We can continue.
All right. Okay. So let's continue with where we left off. So what have we seen so far? Just to recollect. So I discussed how you can construct multi-layer perceptrons, which is the simplest form of neural networks, how you would go about training them, that they have various hyperparameters that you need to somehow figure out how to pick, and also first you to train the weights and biases of the network to approximate some function. And then I talked about some convergence results for the regression problem. And then we went on to the task of actually using data to detect and interpret what the underlying distribution of the data is, and then try to generate more samples from that. And in particular, we looked at generative adversarial networks as a way to learn an underlying distribution from data and generate new samples, which look exactly like those that you would get from the underlying distribution. Now, let's try to see how you can use GANs to actually solve inverse problems. Now, I don't know if I'll be able to cover all these sections, but at least let's begin and see how far we get. Okay. So I know that this might be a little redundant in this workshop, but I really like this interpretation of what inverse problems are, as was said by Joseph Keller. He says that we call two problems inverses of one another if the formulation of each involves all or part of the solution of the other. And often, due to some reason, one of these two problems is studied more extensively, while the other one is newer and not so well understood, in which case you can call the former problem the direct problem and the latter one the inverse problem. So let's look at an example of an inverse problem. Okay, so let's look at an inverse problem in the context of solving elliptic PDEs. So say you're interested in solving this elliptic PDE, which is the steady state PDE for the temperature field U on some 2D domain, say, which is given by this elliptic PDE, where kappa is the conductivity field, B is some source that is given to you, and you assume that you have Dirichlet boundary conditions. Now, what is the direct problem? The direct problem would be given the PDE, given the source term, given kappa, you want to find what the temperature field U is, right? So for instance, suppose your conductivity looks like this, which has got some constant value in the background and has a rectangle which has a linear value going from 50 to 100. So starting from this kappa and this PDE, you want to find what the temperature field is. That's fine. The inverse problem would be if you're given the PD, you're given the source term, and given the temperature field, you want to infer what the underlying conductivity field looks like, right? That means solving the inverse problem over here. Now, there's of course more to this. Some challenges with inverse problems is that, of course, the inverse map may not be well posed, even if the forward map is. Secondly, at times, which is true for most real problems, in fact, you're not measuring the exact output of the forward problem. You're measuring some noisy version of this output from the forward problem, right? And then you have to actually work with this noisy measurement and then try to infer the field, in this case, the conductivity. And finally, if you have some a priori knowledge about the field you're inferring, you need to find some suitable way of encoding that prior knowledge into your inference algorithm. Now, there are typically two main ways in which you can solve inverse problems. One corresponds to regularization techniques, where you would solve for an optimization problem and try to find a single best reconstruction of the field that you're trying to infer. And you could use maybe something like a TV regularization, or you could use something like Tikhonov regularization to get this done. Now, the other method, which I'll be talking about today once I get to it, is the context of Bayesian inference, where not only are you getting a reconstructed field, but you'll be getting some statistics with respect to this reconstruction to tell you how reliable or how uncertain you are about the reconstructed field. And where this could be important would be, for instance, in places where the inferred field and the uncertainty in it is critical for making some high-stake decisions. For instance, if you are doing medical imaging problems where you have to detect, say, the liver lesion from a CT scan, then if you just give the doctor the single inferred field, it might be a little unsafe because you're not telling the doctor how certain you are about the field of the liver image that you've reconstructed. On the other hand, if you give it given a measurement, you're getting an inferred field along with the point-wise standard deviation that's telling you how certain you are about the reconstruction, rather how much spread there is point-wise, then the doctor can actually take a safer decision based on this additional uncertainty for the inferred field. And similarly, you can do something for instance, if you're trying to find infer the basal sliding friction at the base of the Antarctic ice shelf from just measuring the surface ice velocity, because this is critical to figure out how much of the ice is going into the ocean and how much the ocean level or the sea level will rise by, then again, it's going to be important to not just get the inferred field of the basal sliding friction, but also know how certain you are about the basal sliding friction. So these are some applications where having this uncertainty about the inferred field is going to help you make safer decisions. So with that in mind, let's get into Bayesian formulation. So some notations I'll be using. I will be assuming that all the quantities that I'm working with will be discretized on some grid. Okay, so because I'll be using for most of these problems, at least say PD driven, and the solutions will be represented on some discrete grid. Is there a question? Okay, so the parameter that we wish to infer, I will denote as x, which will be on some nx dimensional object. So for instance, if you're solving the heat equation, this could be kappa defined on nx grid points. The measured response from the direct problem, I'll denote as y, which for instance could be the velocity, the temperature field on ny grid points. The direct map going from omega x to omega y, for instance, in the case of the heat equation, it would be the discrete PD solver. That's what the direct map will be. And of course, sometimes you will have the output from the forward map plus some noise, or you have some additive noise. That's actually what you're measuring, where this noise eta is given by some distribution p eta. And of course, we're working in a probabilistic setup. So the x and y's will be modeled by random variables, x and y. Okay, so to talk about the Bayesian formulation, you have to start with Bayes' theorem, which says that the conditional of x given y is the probability of y given x times the marginal of x by the marginal of y. And if we apply this to set up an inverse problem where we're given a measurement y and some prior information, we want to infer the x that leads to that y, then the px of x can be interpreted as a prior information. And there's a prior distribution that you have to somehow construct based on some samples that you're given, or maybe some additional constraints about x that is known. That's step one. Then py given x is the likelihood of observing the measurement given some x. And for the case of additive noise, where you have y is equal to fx plus eta, you can actually write the likelihood term as p eta of y minus fx. And this is a nice way of actually embedding the physics into your inference problem, because f is the forward model that tells you how x leads to an output. Then, of course, you have the denominator over here, which is known as the evidence term, which is used to normalize the numerator. And typically for most high dimensional problems, this is very hard to compute. So we assume that we do not have this evidence term. And finally, the term on the right is the posterior that we're after, which is the posterior distribution of x given the measurement y, right? And since we don't have the evidence term, we will have the posterior distribution of x given y is simply proportional to p eta of y minus fx times the prior of x. And we have to work with this proportionality relation. Now, how would you typically solve something like this? Well, the first step would be you have to explicitly construct your prior px. That is crucial. And this has to be done from whatever data or constraints they give it to you. Once you have this prior, and you know that you're working with additive noise, you know what the likelihood term is, then for a given y, you could generate samples by using a Markov chain Monte Carlo to sample from a posterior, where you would engineer a suitable Markov chain whose stationary distribution is the posterior distribution that you're after. And of course, what's important typically is that you need to burn an initial part of this chain and ignore that, and then work with whatever is left to actually take empirical averages or statistics with respect to it to get the statistics of the posterior that you want. One could, of course, also use variation inference instead of this. But for this talk, I will be sticking to using MC type of techniques to sample from my posterior.
The one question.
Yeah.
So your physics embedding is mainly based on the x function x f of x, but it is not considering the source model from which we get the X.
No,
Yeah.
So in principle, the source model from which you get the X is what you'll actually model into your prior, right? That's
Okay.
from the samples that you have over X.
Okay.
So F is only modeling the direct problem. Yes. Okay. Okay. Now, what are some challenges with Bayesian formulation? First of all, if the dimension of X that you're trying to infer is very large, MCMC can be prohibitively expensive to use. So you really can't use MCMC when NX is large, and it could be as large as 3 million for certain problems. And the second problem is, in order to construct explicitly your prior, you might be given data which correspond to complex samples, right? And we had seen this earlier, that if you want to assume a Gaussian prior, it would make life simpler. But of course, if you're given samples which look like this, which is the microstructure or handwritten digits or perturbed Shep-Logan phantoms, you can't model these kind of samples using a Gaussian prior. And I will show you how you can resolve both these issues using a generative adversarial network. You've sort of already seen what a GAN can do, and we'll see how you can address both these issues with a GAN. Okay. All right. So the first part is using GANs to actually represent the prior. Okay. And recall what we've seen in the first lecture. I talked about this Wasserstein GAN, which has two networks, a generator and a critic, where the generator is trying to create fake samples, and the critic is acting like a cop and trying to discriminate between fake and real samples, and they are trained in an adversarial manner. And what's important to remember here is that the generator takes as input a Z, which has a much, much smaller dimension than the dimension of X. So this actually gives you a way of doing dimensionality reduction, right? This is step one. This will be useful for actually doing MCMC later on. And of course, to train this network, you have to solve a min-max problem where the critic maximizes loss function and the generator minimizes it. And of course, if you work with the Wasserstein metric, you end up with convergence in the Wasserstein 1 distance, which leads to weak convergence, which means that the statistics or the moments of the true and fake distribution will match up. Correct? So this is what we had seen about Wasserstein GANs. Now let's see how you would use it in the context of Bayesian inference. So what you'll be given is a set of Xi's from your prior distribution, right? So let's assume that this sample, these samples are given to you, and you know the forward map F either directly, either exactly or approximately. So this could be, for instance, an FEM solver, and that's what your F is, an approximation of the true direct map. And you also know something about the noise distribution P eta, and you're given some noisy measurement Y. Then what you want to do is determine the posterior of X given Y. And in principle, you want to evaluate statistics with respect to this posterior. And the work that I'm describing here has been done by our group, and details can be found in these two papers. But essentially, this is the approach. Step one, you're given this data set S of prior samples. You train a WGAN to get a generator G star that is able to sample from it. And if you've trained the G star and you have converged in the Wasserstein 1 distance, if you remember, you'll actually end up with this weak relation where the moments match up. So in this case, the moments of X sampled from the prior will be equal to the samples that are being generated, the fake samples being generated by the generator over here, right? So we have this moment matching for the prior. Next, let's also assume that this forward map F and P eta are continuous. And typically P eta can be taken to be a Gaussian distribution, so this is continuous. Then what you can do is this L is any continuous bounded function on omega X. So you can choose Lx as 1 over Q. Of course, we won't actually be using Q, but for the time being, let's plug it in. This Q is the evidence term. So you choose it as 1 over Q L hat of X, where L hat is any other continuous bounded function of omega X, times P eta of Y minus Fx. And let's plug it into this expression for the prior over here. And in doing so, you end up with an expression for the posterior. Because when you plug it in and use the expression of the posterior, you end up with this equality of moments in terms of the posterior of X and in terms of the posterior of Z. And what is the posterior of Z? The posterior Z looks exactly like the expression that you had for posterior of X. So this is proportional. So the posterior of Z given Y is proportional to P eta of Y of F of G star of Z times PZ of Z, okay? And essentially, sampling an X from the posterior is equivalent to first sampling a Z from the posterior of Z given Y, and then pushing this Z through the generator to get a sample in X. And then you can evaluate statistics with respect to this X that the generator is creating. And the good thing over here is that this PZ of Z, you know, because you take it to be a multivariate Gaussian distribution. While in the case of X, you don't know the exact form of what the prior of X is, but you know what PZ of Z is, right? So the step 2 is once you have this approximation in terms of the Z space, the lower dimensional space Z, now you can actually do MCMC approximations for the posterior of Z. And since it's a lower dimensional space, MCMC actually becomes computationally okay to do. And you end up with an MCMC approximation of the posterior. And then the final step is you do some Monte Carlo empirical averaging or to evaluate whatever statistics you want, where you first use the Markov chain generated by the MCMC algorithm, push that through G star to get samples in X, and then you can evaluate statistics with respect to it, right? And this is how you can use GAN as a prior to approximate the prior information, reduce everything to the latent space of the GAN, which is much lower dimensional than in the dimension of X. So you have dimension reduction, so you can do MCMC sampling. So what we gain is, first of all, you can represent very complex looking priors, provided the data set S is available to you, and MCMC computations become tractable because you're doing this in a lower dimensional space. Any questions on this or on this methodology? Okay. So seeing none, I'm assuming that people have understood the idea of what we are trying to do. And so let's actually go and see some actual results to see how well this approach actually works. Okay. So let's come back to the problem I've shown you initially, which is the heat conduction problem, where you want to find the conductivity kappa. Okay. So the measurement would be Y, which is a noisy temperature field U on some 2D grid. The field you're trying to infer is the nodal values of the conductivity kappa. The nonlinear forward map F, which solves the PD, and this is implemented in Phoenix, is going to be my forward map. And the noise I assume to be IID Gaussian, which is added to the measurements. All right, so under this assumption, let's look at a few scenarios. In the first situation, is there a question?
Sorry to interrupt, one question. How many measurements? In the sense that how many different values of so
in the data set?
Yeah, the data set. So it looks like it's just one measurement essentially, right? Because you're only putting the Dirichlet boundary, U of C is equal to 0.
Right.
So it's just one measurement.
Mm-hmm. No, so yeah, so the measurement, so given a particular measurement, you want to infer the corresponding X. So of course, there's just one measurement. So for that given measurement, you want to infer X, correct? So the GAN hasn't come into play here. So you're just given a measurement, you want to infer the corresponding conductivity for that measurement. There's a single measurement Y right now. But you're assuming.
Okay, I see. Okay, but you're measuring this, the
kappa.
Oh, okay, but you're measuring the temperature field on the entire 2D.
Yes,
okay. Right.
Exactly. So it's essentially like an image. So the temperature field is like an image on a 2D grid. Kappa is also going to be like an image on a 2D grid. So you want, given a noisy version of the temperature, you want to infer X from it on the 2D grid.
Yeah. Okay. Thanks.
All right. Okay. So first we have to. Okay, is my screen moving over here? All right, now it's moving. Okay. All right. So first problem is I assume a prior on kappa to train my GAN. So the prior I'm assuming on kappa is that the conductivity field is given as MNIST digits on a 2D grid, where it takes a background value of 1 and a value of 10 wherever there is this handwritten digit. Okay. So this is the prior I'm assuming on kappa. So then this X has a dimension 784 because this is a 28 square grid, and I'm going to train a GAN with Z having only 100 dimensions. And once I train it, these 4 are the training samples, and these 4 are what the GAN is generating for different Z's now. So once the GAN is trained, it is able to generate MNIST type of digits which correspond to the kappa. That is my prior information. Okay. So at this level, you've just trained a GAN on lots of kappas which are given by MNIST digits. Now we will use this GAN on a new measurement of Y, which is temperature field, which will be noisy, and try to infer the corresponding kappa that relates to it. Okay. So what we do is we first start with a kappa, which is not in the training set, and we generate the Y for it. Well, this is the Y without any noise, so we add some Gaussian noise to it. So this is the measurement that will be fed to my Bayesian model. Okay. So given this measurement and using the GAN that you've trained as the prior, I want to then sample in the space of Z's, get a Markov chain, and then take the statistics of G star of Z and get the map, the mean, and the standard deviation. And what you see is this is the map, the mean, and the standard deviation for the posterior. And you see that the map and the mean look very close to the true target kappa, and the standard deviation is showing you that the uncertainty is the highest along the edges of the digits. And if you try to compare this approach to a normal variation inference method where you start with this measurement, this is what you get with the TV regularization. And what you notice is you're clearly not getting something as sharp as what the GAN, or what you're getting with the GAN-based prior, correct? And then we also tried the following. We took another kappa, which was not in the training set, found the corresponding temperature field on the grid. Now we occluded and hid a part of the temperature field and added noise to it. So this measurement, this noisy measurement, is being fed to the Bayesian problem where a part of your measurement is not completely hidden. And then we tried to infer the underlying kappa, and that's the map, the mean, and the standard deviation. So even with occluded data, we are actually able to recover the underlying kappa. And once again, the standard deviation is the highest along the edges of this digit. So any questions on this result? Okay, so let me move on to another example then. Now we come to another example where the prior, I'm assuming on kappa, is that it's given by this microstructure. And this was actually solved by using the Cahn-Hilliard equation to solve for some final time t. And these, we said, is the background kappa to formulate my prior. And then this image is now of dimension 4096. And again, NZ is still kept as 100. We train another GAN on these set of images, and the GAN is generating images like this, which again visually look similar to what was there in the training set. So now that we again have this GAN prior, we will plug it into our Bayesian update step, and we'll use some measurement and try to infer a kappa. So we take some true kappa, not in the training set. We evaluate the temperature field, and we add some Gaussian noise to it. And then we try to evaluate the map, the mean, and the standard deviation. Now, in this case, it gets most of the things correct, but you notice if you look at the areas which I've kind of marked with these red rectangles, you'll notice that the map, the mean, does not really match the true distribution over there. And perhaps this is not very unexpected, because at the bound, if you look at the temperature field, we have directly boundary conditions for the temperature field. And near the boundary, the temperature is primarily determined by the boundary condition and not really by the conductivity. So the signal is low. But what's nice about Bayesian inference is if you look at the standard deviation, are you able to see my mouse move around by any chance? Wait, my screen seems to have frozen.
Yes.
Okay.
Yeah, we can see a mouse here.
Mouse,
Okay.
yeah.
Okay, I don't know why it's freezing in my end. Okay, so now if you look at the standard deviation in those zones where it got things wrong, you'll find that the standard deviation is also high in the regions where it got things wrong. So now you're getting a reconstructed kappa, but with the standard deviation, you're also getting information about how certain you are about the reconstructed kappa. So that's the benefit of Bayesian inference. And again, we did the same thing with another sample of kappa. Again, it got a few things wrong at the boundary, but the standard deviation in those regions was high. And you can again compare this to a usual TV regularization approach, in which case you don't even get the right intensity of kappa. The maximum intensity that we actually got was 12, but it should actually have been 100. So in this case, again, you can see, at least for this example, GAN as a prior is useful because it's giving you a good reconstruction and is also telling you the reliability of the reconstruction at a pixel-wise level. Okay, so if there are no questions on this, I'll move to the next example. Okay, so now let's come to another example, which is not based on a PDE, it's based on an integral equation. So we're trying to solve the inverse radon transform problem. So the task is to find the tissue density rho and we're looking at 2D slices. So we're looking at rho defined on R2, given the line radon transforms, which is the integral over a line which is parametrized by the angle of inclination and the sign distance of the line from the center of the domain. So the problem setup is the following. What we're trying to infer is the nodal values of rho on some 2D grid. The forward map is basically a bunch of these radon transforms. The measurement Y would be the sinogram, or rather the noisy version of the sinogram for these radon transforms. And once again, we'll assume that the noise is Gaussian IID. Okay. And first thing, again, as we've done earlier, we have to assume a prior on X. And the prior we assume on X now is that it's given by these perturbed Shep-Logan phantoms. Okay, so these are the training samples that I worked with. This is of dimension 16,000, much larger than the previous examples. But again, NZ we keep as 100. And then you train a GAN, and then you try to see what the GAN generates, and you find that the GAN actually generates pretty sharp images of the kind that it trained on. So the GAN is learning to generate samples which is similar to the training distribution. And now with this GAN, we plug it into a Bayesian update step, give it a noisy measurement, and see how well it does. Okay, so what we do is we take a true phantom, which is not in the training set, find the sinogram, and this time we add different levels of noise to this measurement to see what the impact of different amount of noise is. And in each case, you can find the map and the mean, and you see the map and the mean are very close to the true phantom, and you find that the standard deviation is the highest along these ellipses, the boundaries of these ellipses. And what you also find is as you're increasing the noise moving up to down, you see that the standard deviation is also increasing along these points. And this is not unreasonable because the more noise you add, the more uncertain you would be in reconstructing the underlying phantom. So this kind of makes sense, right? So even in this case, it's not a PDE, but it's an integral equation, but using GANs as a prior is helping you get pretty accurate reconstructions of your true phantom along with some uncertainty about the reconstruction. Okay, so this was GANs as a prior. So any questions on this? Okay.
So,
yeah.
Deep, I have a question. What about with, if you do like, what's the size of your data?
Yeah. So typically for many of these problems, the size of the data is like 8,000 or 10,000 samples of phantoms, right?
Okay. So by that, I mean the following, right?
Yeah.
When I said about limited data in the following sense, that you said that you have a bunch of line transforms, correct? But I suppose this bunch of line transforms are evenly in the sense that these lines are randomly picked, in the sense, right?
No, so the way I picked it for this problem at least is I took 128 equally spaced angles, and for each angle I had 128 parallel lines equally spaced in space.
Okay, so now, but this 128 that you are mentioning is over this 0 to pi. Yeah,
0 to pi, and 128 also for 128 lines for each angle. Yes.
Now, what I'm wondering is what would happen like if you do not go from 0 to pi, but you only go to from 0 to pi by 2, right? So this would be like a limited data problem. And the thing is, mathematics tells us that the reconstruction is not going to be good, right? And it would have been, it would be interesting to see how this, this particular approach would actually perform the reconstruction.
Right. So we have not tried that. What we have tried is making the measurement sparser. So instead of 128 cross 128, we have done something like 64 cross 64 or 32 cross 32, taking a much sparser measurement and try to reconstruct the phantom. But what we haven't done is take the reconstruction or take the sinograms only from 0 to pi by 2. That's something that might be worth trying to see if we're still able to reconstruct the underlying phantom.
Okay. All right. Yeah. Thanks.
All right. Yeah. Okay. All right. So this was Gans as a prior. Now, there are two things to note here. So the way it works is, first you're given these bunch of x's, you train your GAN, and then you plug it into your Bayesian formulation. And then what you have to do is you have to generate this Markov chains, correct? And to generate the Markov chains, if you remember the likelihood term over here, let me go to the likelihood term. Yeah, the likelihood term has the forward model F sitting in it, correct? And the Markov chain, you typically have to take 30,000 or more iterates of the Markov chain to actually get to something that's converged. That means you have to take as many forward solves to actually generate the Markov chain. As this forward map is expensive to evaluate, your Markov chain will also become quite expensive. And as soon as you take another measurement y, again, you'll have to take 30,000 or more forward solves to get the Markov chain. So this can become quite tedious. And of course, a Markov chain, Monte Carlo, is not the easiest algorithm to actually train. There are hyperparameters associated with that, and it can be difficult to also train those. And you have to simulate them for a very long time till you actually get something that is converged. So the question is there a way of completely circumventing the use of Markov chains and directly being able to sample from the posterior? And the answer is yes, and that's going to be the next way of which you can use GANs. And that is Gans as a posterior. So I'm guessing I do have around another 20-25 minutes, right?
Yes, that's correct.
All right. So good. So we can actually get into Gans as a posterior. All right. So to understand Gans as a posterior, we actually have to look at a slightly different kind of conditional GAN. And these are GANs which learn distributions conditioned on some other field. And this conditional Wasserstein GAN is based on the work by Adler and Al-Mahiri. Adler used this kind of a conditional GAN to work from to use a filtered backpropagation from a sinogram and then try to reconstruct a high resolution image or phantom from it. But we are trying to use this to actually solve physics-driven inverse problems. So what does a conditional GAN look like? Now try to recall what this is compared to the GAN you've seen earlier. So once again, you will have a generator, you will have a critic, but now the generator not only takes as input a Z, but will also take as input a Y. And in this case, you'll have X and Ys, which are sampled from the joint distribution PXY. Okay, so in this case, the data set will also be sampled, pairwise samples from the joint distribution. So this Y will correspond to some true XY pair from the joint distribution. So you feed in the Y, feed in the Z, the generator, and the generator again gives you a fake X tilde. Then the critic, now instead of trying to simply distinguish between fake X tilde and true X tilde, it will try to distinguish between fake joint pairs and true joint pairs, where the Y for the joint pairs will always be the true Y. What will be fake is the X component of the joint pair, right? So in this case, the critic will take as input something from omega X cross omega Y, and for true samples XY, it'll try to take a large value, and whenever it's not a true sample, it'll try to take a small value. So it's going to try to distinguish between fake and true joint pairs, okay? And in this case, you can construct a similar loss function using the Wasserstein distance, which will look like this, where the expectation is going to be taken over joint samples X5 from PXY, and Z sampled over your latent space. And again, you would try to do, the critic would try to maximize this and the generator would try to minimize this. And you would try to solve this min-max problem under the constraint that D is 1 Lipschitz. And what you can show is for the optimal generator G star that you're getting for this, for a given Y, G star for that given Y will actually be minimizing the Wasserstein distance between the conditional X given Y and the push forward of PZ by the generator for that fixed Y. So for a fixed Y, the optimal generator will actually be minimizing the Wasserstein 1 distance between the target conditional that you want and the push forward for a fixed Y. And convergence against in the W1 metric will imply weak convergence. So what you can show is the expectation of L of X, where X is sampled from the true conditional X given Y, is going to be the same as the expectation of L of G for Z comma that given Y, where Z is sampled over this latent distribution PZ, correct? So what you will typically do is once the GAN is trained, you will fix a Y and you will take lots of samples of Z for that fixed Y. So you'll correspondingly get lots of samples of X, and those X's will correspond to samples from the posterior. And then you can take all kinds of statistics for those ensemble of X's that you've got for that fixed Y. Any questions on this? Any questions on this architecture? Is this part clear that it's taking an input Z and Y, and you fix a Y, take lots of samples of Z for the fixed Y, and you get lots of X's?
Deep, here it will not influence by the same kind of error which occurred in the MCMC method, like curse of dimensionality, etc.
No, because what you're doing is you're fixing a Y, but you're still sampling over Z, and Z is still low dimensional.
Okay.
Right? And in this case, the way you would compute your statistics is first you will start with the data set S of XY pairs, where XI will be extracted from some prior, and YI will be taken from Y given this XI. In principle, what you would do is if you have the forward model, you would plug the XI into the forward model to get the corresponding YI. And this XI and YI would correspond to a pair from the joint. And then you're given some new noisy measurement Y, and you want to still determine the posterior of X given Y and evaluate statistics with respect to it. So you first train again on this pairwise data set to get the generator G star Z of Y. And then you can actually show that the posterior moments will match when you fix the Y in the generator, okay? And sampling from X from the posterior is equivalent to fixing a Y and sampling Z from PZ and evaluating X at G star of Z comma Y, where Y is fixed, okay? So you're getting samples, and then there is no longer any MCMC. You can directly take Monte Carlo statistics of the G star Z of Y that you're getting. So the advantage is, again, you're able to represent complex priors if the data set is available. You have dimensionality reduction because NZ is much, much smaller than NX. But now you're only sampling from the GAN when it's trained, and there is no longer any MCMC. So sampling becomes much simpler.
Okay, one more thing is, here we did not consider the covariance of Y.
No, we didn't have to consider the covariance of Y, no.
Okay.
Okay, any other questions? Okay, if not, now let me show you some examples. So this is some work that we are recently doing, so it's still work in development. So let me show you some results that we have. So again, let's come back to the heat equation problem, okay? But now we are solving this problem with GAN as a posterior, so there's no MCMC. So we still want to infer the nodal values of the conductivity kappa, given some noisy measurement of the temperature on a 2D grid, which is Y. And we generate samples by sampling from some prior knowledge we have about X and evaluating Y is equal to Fx plus eta. So we have the forward model, we push the X through it, add your noise, and that gives you the Y pair for the corresponding X. That gives you your data set S, and then you train your WGAN, conditional WGAN, on this pairwise data set S, okay? And once you have this, then all you would do is you would fix the Y, take lots of samples of Z for that fixed Y, you'll get an ensemble of X's, and you will take the mean and standard deviation pointwise for that particular X. Let me show you how this can work for a particular kind of prior. So in this case, we assume the following. So we're assuming that kappa is given by circular inclusions. So it has some background value of kappa, and on the circle, it has some value of kappa. And what we assume is this circle can take a random position in your domain, and even the size of the circle can be different. So you use this kappa, you solve the heat equation problem, and you add noise to it. That gives you the y. So basically, each of these will be the xy pairs that will be there in your training set S, right? So this will be the x's, the y's. Here again, this will be the x's, and that will be the y's. Okay, so this is the xy pairs that you've generated a priori. And in this case, both x and y will have dimension 4096, but nz is only going to be 50 dimensional. So once we train a GAN, we'll see how that GAN now works for a new measurement which it has not seen. Okay, so we solve the inference problem. Then we take a target kappa, which the GAN has not seen before. You form the noisy measurement, and you feed this to the trained GAN. Take about 200 samples of Z, which is easy to do. You get 200 samples of X. Then you take a pointwise mean and standard deviation. And you can see that the mean actually captures the target distribution quite well. And once again, you see that the standard deviation is actually peaking at the boundary, in this case, of the circular inclusion. Now we tried another problem. Again, we took the kappa, solved the heat equation, added some noise to it, and then we tried to sample 200 Z's and get the mean and the standard deviation. In this case, it actually did make an error. It's not completely circular over here, right? It should be a circle, but it doesn't look circular. But what's nice is you also find that's the same region when the standard deviation also takes a higher value. So again, you have uncertainty in the reconstructed state. So we are able to recover these circular inclusions once you've trained on circular inclusions and kappa and the corresponding noisy y's for the GAN. Any questions on this? Okay, so now after this, we try to ask the following question. How much can we push this GAN? Can it actually generalize beyond the data set it has been trained on? Wait, there is actually a question in the chat. Let me see. Is there a way to know how the noise level in there a way to know how to know the noise level in a given data set? I mean, in experiments, generally we are synthesizing the noise. Yes, so typically, if you look at GAN as a prior approach, it is known that this Bayesian inference is robust to the kind of noise you're assuming. So what we have done, for instance, is we have generated the data with some kind of noise, and then we assumed a very different noise in the likelihood term. And in that case, we found even then you were getting very good reconstruction. So it is robust to getting the noise model slightly wrong. But of course, otherwise, if you're given a measurement, there is no way of knowing what the true noise model is. It need not even be Gaussian. But Gaussian is typically what you choose for measurements when you solve the Bayesian problem. Does that answer your question, Murali?
Yeah. Thank you. Yeah. Right. Basically, I was wondering because in the industrial applications, in the inverse design problems or something, we have been given the measurements and we want to reconstruct either some kind of boundary or something like inverse geometric problems.
Right.
So how to know, suppose I'm applying some method, how to know, okay, not just by machine learning or some method, how to know the reconstructed data, we are obtaining that nicely, like the method works nicely for those kind of, suppose noise level is 10% or something that I don't, and how to know that the results that I'm obtaining, that is that the method is working properly or not for that.
Well, honestly speaking, I mean, if you solve the problem and you get some inferred field, the only way to know that the method of design is working well is that you first tested it on data where you do know the underlying field you're trying to infer. So you first test that method out on some situations where you know what the underlying inferred field must be. Otherwise, there is no way of, I don't see any way of knowing that the field that you've inferred is the correct one if you don't have any information on that. Okay. So you should test it out on something else first. If it works well, and you have some faith in the method on some test problems, then I would move on and try it on some problem where I don't know what the X is to begin with.
So that's why we are synthesizing the data here, always in the experiments.
Yeah, so in this case, we are synthesizing the data. I haven't shown one example, which is there in the papers I talked about, where we actually took some experimental data, where we worked with our collaborators and they gave us it was an elasticity problem, and they gave us the measurements from a synthetic phantom, from a prosthetic phantom they generated in the laboratory, and they'd given us the measurements. In which case, of course, there's no way of knowing what the true noise is in the measurement, but we were still able to generate the underlying phantom from that. Okay. So it still worked pretty well.
Yeah, I have one more small question.
Sure,
so
go ahead.
Here we are assuming like this kind. So suppose there is some lack of data somewhere, like embedding kind of stuff. So this GAN will work in that cases?
Well, we have tried the previous approach. If you remember, I had shown an example where we had missing data, right? So if you remember this example, let's see if I can go back, right? Here we were actually taking measurements where we're missing a big chunk of the measurement. It's not known.
Okay.
But you're still able to reconstruct the underlying inferred field, even with missing information like that.
Okay.
We haven't tried the second approach with this, but it's something that we want to do more tests on and see if we're able to recover with missing information. We are trying it for some other kinds of problems where there is inherently missing data. And there are certain GANs which are designed to recover or to train on data which is incomplete and then generate the full data from that itself. So there it's called an ambient GAN. If you want, you can have a look at that. An ambient GAN is actually able to generate missing data when it's trained only on missing data.
Okay. Thank you, and sorry for interruption. Yeah.
No worries. Okay, so here I trained a GAN on circular inclusion that seems to work well. Now we tried to test this out in a scenario where we actually had two circular inclusions. So the GAN has not been trained on this. So the target is these two circular inclusions. We find the temperature field, add noise, and then we try to recover the mean and standard deviation. And surprisingly, the GAN actually was able to detect that there are two separate circular inclusions. Of course, it got the size perhaps of the smaller inclusion incorrect, but that's also where the standard deviation is higher. And what we found is as you bring the circular inclusions closer to each other, after a point, it no longer detects the second smaller circular inclusion. So what it seems is the GAN, in trying to learn the inverse map, has learned some local nature of the map. So if these objects are far apart, it's able to identify them as different objects. But if you bring them too close to each other, then they're no longer far apart. And because the local nature of the map, it's not able to distinguish between these two separate inclusions. But of course, we're still trying to test out this argument and see if it holds true. We're trying to show this mathematically as well. But we are seeing that you are able to generalize better, even on samples or out of distribution samples, which is not there in the training set. And we tried something similar now for solving the time-dependent heat conduction problem, where in this case, we have kappa, which is constant. We have a zero source term, but we have an initial condition. And we're trying to solve the inverse problem where if you're given the PD and the final temperature at some time t, we want to infer the initial condition. And this is the severely ill-posed problem. But we want to see if you're able to actually use a GAN to recover this U0, given the temperature at final time t. So the inferred X would be the initial temperature field U on the 2D grid. The measurement Y will be the noisy temperature field U at the final time t on the same grid. We again generate samples by taking lots of X's, evaluating Y by pushing it through the X, which is the PD solver, and adding noise to it, and then training a GAN on these XY pairs. And in this case, we assumed that my initial condition was again given by these MNIST handwritten digits. So we used this as the initial condition, solved the heat equation in time, got the final temperature at time t is equal to 1, added a lot of Gaussian noise to it. So at this level, you can't even see the digit. And then given some new measurement, we want to see if we can recover the underlying digit. And we did this where we looked at 4 different digits which are not there in the training set. So this was the target. This was the corresponding noisy measurement. We pushed it through the GAN, took 200 samples of Z for this given measurement, and found the mean and standard deviation. And we find that we are actually able to do a very good job at recovering the underlying target initial condition in this case. And once again, you see that the highest uncertainty seems to be along the sharp transition zones of the initial temperature field. And then once again, we try to ask the question, can we actually generalize this to work on out-of-sample distributions, which look something like handwritten digits, in the sense that they'll still have a bi-total distribution of value in the background and some value on it, and see if you're able to recover the underlying initial condition. So what we did is we worked with something called as the not MNIST set. So these handwritten digits are called the MNIST set. These characters or font alphabet are known as the not MNIST set. So we worked with something where this is the target distribution. Of course, this is far from anything that the GAN has seen. This is the measurement, and we tried to infer what the mean and standard deviation is. And of course, we don't get a very good reconstruction, but it's interesting to note that although the network has been trained only on handwritten digits, it's actually able to recover something that looks not like a digit, but like the underlying A that you're working with. And in this case, since a lot of the information, even the interior, was incorrectly determined, we find that even the standard deviation is high, not only at the boundary, but also in the interior of this A. And similarly, we did something for the E, and we were able to sort of figure out something that looks like an E, not a digit. And in this case, again, the standard deviation is quite high in areas where it's not getting things correct. Okay. Any questions on this? Okay. So this was the two approaches. I talked about GAN as a prior and GAN as a posterior. Again, are you able to see the slides? Okay, there you're able to see the slide. It's updating slowly on my end. Okay, so we saw GAN as a prior and we saw GAN as a posterior. So it'd be good to compare these two approaches. How do they differ? So in the first case, when you're talking about data generation, you only needed X's from the prior distribution. In the case of GAN as posterior, you first needed X from the prior, and then you needed to find the corresponding Y sample from Y given X, which is essentially obtained by pushing Y through the forward model and adding noise. So you needed pairwise samples for GAN as a posterior. So I guess in this case, GAN as a prior is a winner. Then you talk about the forward model and where it's used. So for GAN as a prior, you need both F and the derivative of F with respect to its input in the MC sampler, because we are using a Hamiltonian Monte Carlo sampler, and that actually needs derivatives of a forward map as well. And this essentially means we need to differentiate or use automatic differentiation of a PDE solver. And that's a nightmare to do and couple with training algorithms. But in this case, we need F and del F by del X. But in GAN as a posterior, once you've created your data set offline, you do not need F anymore. Okay, so in this case, GAN as a posterior is a winner. Then the first case, you need to sample both from the GAN and the MC algorithm or a chain. While in the second case, you only need to sample from the GAN. So it's simpler to sample from. In the first case, generalizability in terms of how well it performs out of distribution samples, it's hard to control, because when you're training the GAN, you're only showing it X's, you're not showing it any Y's. But in GAN as a posterior, there is ways of actually getting better control of how it's able to generalize beyond the data set it's been trained on, even on out of distribution samples. And I kind of showed you a few examples where it seems to work better. We actually tried the same experiments with GAN as a prior. And for instance, if you look at this experiment, if you use this as the measurement for GAN as a prior, we actually saw that the mean and the standard deviation actually looks much more like a digit than a letter. So GAN as a prior is not able to actually generalize as well, but there are ways of generalizing GAN as a posterior. Okay, so with that, I come to the final remarks of the lecture. So I've shown you that how you can construct multi-layer perceptrons, and that neural networks, because of various theorems, are good universal approximators. Then I showed you that GANs can actually be used to learn distributions from data and generate new samples from it. Then I showed you two ways in which GANs can be used to overcome challenges in Bayesian inference. One is GANs as a prior, and the other is Gans as a posterior. And Gans are able to capture complex prior information while giving you dimensionality reduction because you are posing everything in terms of the latent space of the GAN, which is much smaller dimensional compared to the dimension of X, which is trying to infer. Then you're also able to generate point-wise estimates to quantify the uncertainty, which is nice. And I've only shown you 2 types of GANs. There are perhaps 50 kinds of GANs which are available out there in literature, each designed for a different kind of application. For instance, I mentioned the ambient GAN, which is useful for sampling when you're working with incomplete data. There are also GANs that are used to convert one style to another style. For instance, if you're doing CT scans, and if you have a flared image of your brain, and you have a T1 image of your brain, then you can have GANs that can, while doing UQ, convert a flare image to a T1 type of image. And finally, although I've only talked about GANs, GANs are not the only generative algorithms out there. There are also variational autoencoders, or VAEs, which can be used to generate new samples. You have something called normalizing flows, which are also very useful. And you have deep Boltzmann machines and many others out there. So if you're interested, I'll be happy to give you, share various references of where you can read about these other methods. But of course, the one that we have been primarily working with is GANs, and we have a better understanding of. So I'll end the lecture over here, and I'll be happy to take any questions that the audience has.
Thank you, Deep. Any questions from the audience?
I have a question.
Sure.
Do these neural networks approximate the subular functions?
Yes, there is actually some work that has been done to show how well you can approximate subular functions with neural networks as well. You have, I think with p is equal to 2 at least, there are some papers out there that can tell you that you can approximate subular functions. I think there is a paper by Yarotsky himself where he's talked about this. In fact, there's something called deep operator networks, which actually learn maps that go from operators go from functions to functions, and that is useful in solving PDEs for any given data or any given source term. And in that case, you can actually use the fact that these solutions have some Sobolev regularity, and that actually helps you get better convergence rates for these deep neural networks. So in short, the answer is yes, you can use it, and there is some work done there in that direction.
Thank you.
Yeah, this GAN as posterior can be used for non-Gaussian distribution also?
Non-Gaussian in the sense, you're talking about the noise model, or you're talking about something else?
Yeah, means suppose my X and Y both are from the non-Gaussian distribution. So
Absolutely.
then GAN as is okay.
Because here the X is definitely not from the X are the handwritten digits. This is definitely not from a Gaussian distribution. And the Y, of course, will also not be a Gaussian distribution. It could be any distribution. I haven't shown you many other examples you've tried. We've tried things where the noise that you're adding is not even additive noise. It could be non-linear noise that you're adding, but it doesn't matter. All you need is these pairs X and Ys, and you can train a GAN with that and sample from the posterior using this conditional GAN.
Okay, even their errors means distribution error. There is no restriction on the distribution error also.
No, there
means,
is
no. Okay.
There is also some work done about which tells you what the approximation errors with GANs are in terms of the number of samples, in terms of the number of trainable parameters, and that work is also available. But of course, it doesn't easily tie to the networks you actually train, because there's a big disconnect between the theoretical results you get for neural networks and the networks you actually train. So unfortunately, there is a bridge that still needs to be crossed between the optimizers and the networks which are used to prove things in theory.
Thank you.
Any other questions? Okay, if not, thank you very much, Deep. It was very nice to set up lectures.
It is a pleasure.
And yeah.
And I'll be sharing these slides, of course, and I've put a lot of references here for anyone who's interested in reading about GANs, reading about neural networks itself, and you can feel free to look through these. if you think these will be useful for what you're doing.
All right. Yeah. Thank you. And please feel free to sign off from here. Okay.
Okay. All right.
Yeah. Bye-bye.
Bye.